Okay, what we want to do here is we want to actually start using statistics. And by statistics, I mean we're actually going to use data to support or reject certain claims, which is really what the class is all about and how you're going to end up using this material in this course in the future and in your future jobs. Okay, the idea here is we start with a hypothesis. Hypothesis is just a guess, it's a claim, it's something that we're trying to prove or don't prove, though of course we don't actually prove anything in this class or any other class that has to do with statistics. The reason for that is because proof is when you know for certain. In statistics we never really know for certain, we just have support or lack of support for any particular claim. So, what are we trying to prove, or in other words, what is our claim? That becomes our alternate hypothesis. The way we set this stuff up is we set up what we want to prove or our claim as the alternate hypothesis because that gives us the lowest probability of mistakenly accepting a claim when the claim is actually wrong. So what we do is we set what we want to disprove as what are called our null or our basic hypothesis. We call it a null hypothesis because most of the time it takes the format of there has been no change or there is no difference. So that what we're trying to show in cases like that would be that there is a difference. So if we reject or find no evidence to support that they're the same, then we could say, gosh, it sure looks like there's something different going on. So that's how we set this stuff up. I know it seems weird, but just roll with it. It does work. All right, first question we have to ask. What sort of hypothesis is this? Are we trying to find a greater than or less than situation? For instance, say the latest model of car coming out of Detroit says that it has a minimum gas mileage of 25 miles a gallon. Well, in that case, what you're trying to prove, quote unquote, is that the gas mileage is at least as large as a certain amount. That will actually become our null, not our null hypothesis, but that will become our alternate hypothesis, so that we use the less than or equal to as our null hypothesis. Again, I know it seems a little strange, but basically we set our null as the opposite of what we're hoping to show. Because by doing that, the way these tests are constructed, we actually have the strongest evidence on our side. If we get around to rejecting the null that there's no difference, we can say with quite a bit of certainty, though not absolute certainty, but quite a bit of certainty, that there really is a difference. So we simply set them up this way. If you want to know more, read about type 1 and type 2 errors in the book. They're not really of much use in the real world. I'm just telling you how to set this stuff up. Now, if all you care about from your data is it different from what it used to be, bigger or smaller, then we have what's called a two-sided or two-tailed test. And our null hypothesis will have this sort of equals to sign down here, and our alternative hypothesis is simply that it is not equal. Now, what formula will you need? Well, that one gets to be tricky because it turns out we're going to get a lot of formulas. For this part of the course, it really gets kind of cookbooky. There are a whole bunch of formulas both in the book and that we'll talk about and use in your homework, but you have to decide which one you want. And in order to decide which one you want, what you do is you're actually kind of going to go down a decision tree. Your decision tree starts with thinking about each observation of your data. What does each observation look like? Is it a yes or no? Like, is the person you interviewed male or female? That gives you a yes or no question. Are they male? Yes. Or are they female? Yes. Another yes/no question might be if you ask somebody if they are a Democrat and they say yes or no. Another one might be, say you ask a survey question of, have you ever flossed your teeth with your own hair? By the way, it turns out that approximately 11% of people in the United States have flossed their teeth with their own hair, which is sort of disturbing. But anyway, the answer to the individual observation question is a yes or a no. The alternative to a yes or no answer for each observation is a number, like how many pairs of shoes do you own? Or what's your income? Or how old are you? Each of those observations gives you a number. Okay, so once you've made that distinction, we can go on. here we have the picture, which is our first kind of decision tree. We're starting with a test. We start with a claim. We ask ourselves, is the data a number? If the data is a number, we refer to it as a normal test or a test of a mean. We'll also find out later that you can test standard deviations, but most of the tests we do will be of a mean. If the data is a number format, like how old are you, or how many college credits do you have towards your MBA, those sorts of things. If, on the other hand, your data is a yes-no, like are you female, yes or no, then you have the situation where you have what's called a proportion or proportion test. In that particular case, what you're looking to test is the percentages of yeses or nos in your data. Now, you have to be careful here because you pick one question, like, did you vote Democrat in the last election? That is your yes, and that's the number of yeses that you count over the total to give you what we'll call later a sample proportion, or the percentage of yeses. Of course, if you have a percentage of yeses, everything else must be other than a yes or a no. So you look only at the percentage of yeses. But that's the first question. What kind of data do you have? And that sets you on your road. Now, if you have these yes-no types of data, what you have is a proportion, and you start by calculating this sample proportion, the number of yeses over the total number of questions in your sample, and you use this as your hypothesis and what you're going to test. For instance, in this class, we could go around and survey and ask how many of you are female. Every time we get a yes answer, that's a 1 or a yes over the total number of people in the class. Now, if there are 25 people in the class, there might be 12 of you that are female, in which case what we have is a sample proportion of 12 divided by 25, or a sample proportion of 48%. We then might have a hypothesis that says, okay, is that number, that 48% sample proportion, the same as the proportion of females in last semester's class? Well, last semester's class we knew exactly what the proportion was, and say it was 52%. So what we want to know is, in this sample, is my sample proportion close enough to last semester to be considered the same? In which case it's an equal to or two-sided test. Or are we going to say, gosh, the percentage of women is growing? In which case we're looking to find out, is the percentage of females increasing? So our null hypothesis will actually not be that it's increasing. Our null hypothesis will be that it's decreasing, because if we can reject that it's decreasing, then it must be increasing. So here's our little lower half of our decision tree on proportions. We do have to ask ourselves if our data comes in one data set or two. Now, the way you find this is by reading the question and finding out if you have two separate sets, like last semester versus this semester for percentages of women, or say whether we're just going to test this semester's proportion of women in this class relative to what the MBA consortium says as our percentage of women in the whole program, in which case we have one data set and we compare to one known point. Basically, count the number of n's in the problem. If the problem is reading out of 15 over here and then out of 30 over there, you've got two n's, where n's are number of observations, and you have two data sets. If it says out of this many n over here, out of 40 on this group, is it the same as what we had 12 years ago that was 43%? If they don't give you a second n, you only have one data set. Now, what happens if the data is numerical in nature? If it's numerical in nature, what you're doing is you're testing for an average, you're looking for a mean. So you're looking to find out if the mean is equal to a certain number, greater than or less than to a certain number. For instance, if we are looking at the number of people that walk by a certain corner, and we're trying to decide if whether that corner would be a good place to open up a hot dog stand, we might want to find out if there are enough people walking by that corner to support the hot dog stand. Well, in other words, what you're looking for is you're looking to show that there is at least as many people going by as some fixed number like 15 an hour. If so, our null hypothesis will be that it's less than that, and if we can reject that null hypothesis, it's a one-tailed test, and we'll be good to go. Now, the second question, this one's pretty tricky when you've got numerical observations, is how do we have a standard deviation? Does the standard deviation come from the sample data, or is it somehow known to be the population standard deviation? Now, the easiest way to find out is if you're given a whole bunch of numbers from a data set and you actually calculate it yourself. You know, as in put it on Excel and type in equal to STD-DEV, and then you put in the numbers and it gives you a standard deviation. That's a sample standard deviation. That's pretty clear. However, what happens if the problem gives you the standard deviation in writing and you didn't calculate it yourself? If it's given to you in writing, it might still be an estimated sample standard deviation. How do you know that? You have to read really carefully. For instance, I've put on this little slide here an example of a phrase that might tell you that it's a sample standard deviation. For instance, let's say the question reads, so-and-so went out and took a sample of 47 people and found a sample mean of 80 with a standard deviation of 6. If they're using the phrase with a standard deviation, that means the standard deviation came from the sample and you have estimated standard deviation. Think about that one. You have to be really careful. That's very tricky. Once in a while, you'll be told that the standard deviation is known for some reason, in which case it may say something as clear as assume the standard deviation is the same as, or assume a known standard deviation of, in which case you assume that you have the population standard deviation. Okay, so here we have, when we're testing data that is a number, it's called a normal kind of test. This is testing for a mean. And when we're testing for a mean, we have either one or two data sets, and then we have to decide if the standard deviation is known or the standard deviation is estimated. Now, there's something special going down there on that lower limb where it says two data sets, standard deviation estimated. You then have to decide whether your data set is one large group where each person or individual gets tested twice, or whether it's two separate groups of people. Stay tuned to the next chapter to find out how to deal with that, but it does matter. Okay, so one data set or two, and when it's two data sets, do you have one group that's observed twice, or do you have two separate groups where each group is only observed once? That makes a difference. Here's the final picture. This is your path to the correct formula. If you go through this decision tree, you will end up at the right place, you'll find yourself the correct formula, and you're absolutely good to go, because at that point all you have to do is really plug in the numbers and the decisions pop right out in your lap. You gotta love problems like that. So anyway, this is the tricky stuff. It's deciding what formula to pick. So think through this issue carefully, and then we'll find out how to use the formulas.